like to tell me, what do you notice about the de Broglie wavelength of a baseball? Yeah, it's really small. A wavelength of 1.4 centimeters to the negative 34 meters. Can you tell me what's special about that? What's that? I mean, if I threw a baseball, would you notice that wavelength? If I threw it through a doorway, would this equation mean anything if I threw the baseball through the doorway? No, because the D is gigantically huge compared to lambda. This is essentially zero, which means my angle of diffraction is zero. It's telling me that if I throw baseballs through a doorway, they're going to behave like this. They're just going to come out like that, right? There's not going to be any diffraction pattern because it just shoots out like that because that angle theta is essentially zero. Okay, so we don't experience de Broglie wavelengths in our normal life, but you sure can experience them when you fire electrons through a crystal atom. Okay, all right, so that's it for de Broglie wavelength. So now it's time. Oh, you just got finished?
Yes.
All right. So let's go ahead and do the next thing. Line spectra. We'll be doing this till about 4:15. Yes. Yes. That baseball is like a wave, but the problem is the wavelength is so incredibly tiny that you can't notice it. It's just not noticeable. And you try to fire a baseball through a doorway, hoping to get interference fringes, and you're not, because the doorway is so huge compared to the wavelength of the baseball. Exactly. Yeah. So that rather than getting this diffraction that looks like this, you're just getting this. The wave is just, the baseball wave is just going to shoot right through. So you shoot a billion baseballs through that doorway, and you'll get a billion baseballs hitting the screen right there. You're not going to get any diffraction patterns, interference patterns. First bright fringe, second bright fringe. That's not going to happen because there's no diffraction happening. Like when I had my Young's experiment right here. Alrighty. Hey, line spectra. How you guys hanging in there? I appreciate you coming. I appreciate you all showing up. It makes me feel very good. Have you guys ever done flame tests? Like you dip your metal wire into some material, then you put it over a Bunsen burner and see what color it flames? Have you guys done that sort of thing? Okay, good. That's related to what we're going to talk about here, which is called line spectra. That is gases, when you excite a gas, and you can excite the gas in any way you want. With the flame test, you're burning the gas, you're putting it at a really high temperature, okay? But you can excite the gas by putting a voltage across the gas, like you see with a fluorescent light, or you can excite the gas by hitting it with photons, by shining a really bright light or really high frequency light on the gas. However you want to excite it, it turns out that this gas will give off light of very specific frequencies. And those frequencies are called a line spectra, or line spectrum of the light. Here's what I'm talking about. Remember those yellow sunglasses you had on our diffraction experiment that turned everything into rainbows? Remember those glasses, like diffraction grading glasses?
He has like 20 of those
What
on.
the diffraction grading glasses do is it takes white light and separates it into its rainbow. So you see all the colors of the rainbow. You would see, red here, and then yellow, and then orange, and then green. You can get all these colors up here. And green, and then then finally you get your violet, you know. I'm gonna make violet be like darker blue. Does it look like violet on the right? No, but imagine it is. So with those glasses, you got everything. You got all the colors of the spectrum, okay? And you got essentially every frequency. You were getting every single frequency of the spectrum when you were looking at white light through those glasses. Well, what happens if you excite a gas or burn a material or whatever? It's only giving out some frequencies of light. That is, it's not giving out all the frequencies like the rainbows you saw. Imagine you burned, you excited a gas or burned some powder or whatever, and it gave off this particular frequency of red, that particular frequency of red, maybe this particular frequency of green, and maybe, these two frequencies of blue, and that's it. But that would be a characteristic of this gas. Whenever you excited this gas or burned that material, you always got just those specific frequencies of light and none other. Now you put them together and it might look white or it might look red or green or blue or whatever, but when you look at it through those glasses, you only get those specific frequencies of light, okay? Well, there's a name for this. It's called the line spectrum, right? And it's called a line spectrum because you're just getting lines, specific lines of color. You're not getting all of them. You're just getting specific ones. And Joel, what were you thinking? Because I saw you laughing. Tell me, because I know you guys learned it in this minute. I like to hear what you do. Oh, another go. Okay. Yeah. Good. That's right. That is, in fact, that photoelectric thing is black body radiation. But it's not part of the AP curriculum, so I'm not going to teach it to you. Yeah, don't have to, but I will. Okay, so that's your line spectrum. Okay, and so then along comes a guy named Niels Bohr, and he says, I know why these specific frequencies of light are given off when you excite your gas molecules. And here's what Niels Bohr's theory was. He says, you've got your nucleus, and you've got electrons orbiting the nucleus. Okay? They're orbiting the nucleus however they want. Okay? They're orbiting the nucleus. When you input energy to this atom, then an electron is going to jump to a higher orbital. That is, it will jump to an orbital that's farther from the nucleus. It's an orbital where it has more energy now, because it's going faster, okay? But in order for an electron to jump from one orbital to a higher orbital, you have to give it precisely the right amount of energy. That is, for example, if you're going to provide the energy by hitting it with a photon, it's got to be a photon with precisely the right amount of energy. If you hit it with a photon with too much energy or too little energy, not going to do it. It's got to be a photon of just the right amount of energy. Then it will jump to the next highest level. After being in this high level for a while, that electron will fall back to a lower energy level, and in so doing, it will emit a photon of precisely the energy that caused it to jump to that higher level in the first place. Do you see that? So let me make a better drawing. This is actually not a good drawing. Let me make a cleaner drawing of this phenomenon that Niels Bohr postulated. And I'm going to simplify it by only addressing the hydrogen atom now. So we are dealing now with the hydrogen atom. You've got one proton in the nucleus. You've got one electron orbiting it. Okay. If I hit this electron with a photon of just the right energy, then this electron will jump up to a higher energy state. or a higher energy level. And now this electron is traveling on this energy level. Until some point where the electron falls back to a lower energy level. And when this electron falls to the lower energy level, then the electron will give off a photon of the same energy that caused it to jump to that higher level in the first place. So what you're seeing with these line spectrums, or line spectra, is electrons falling to lower energy levels. You've excited them, okay? And so they've absorbed energy of some way, and now they're getting unexcited and falling to lower energy levels, and in so doing, giving off photons of just the right frequency, and that's what you're seeing right here. Now, Dawson, yes?
How much longer does it, how long does it take for it to jump back down? Is it instantly, or is it
I don't know. You know, for example, fluorescent lights. I mean, because they turn on immediately, and that's what fluorescent lights are. You're exciting the gas, then the gas electrons are falling to lower energy levels and giving off photons. It seems to happen almost instantaneously. So it doesn't seem to be like it's not holding on for a long time. It's just this constant process of exciting and falling, rising and falling, rising and falling. Yes?
No, I say like some light bulbs when you turn them on, they take a while to like really, light up.
Yeah, that's because it takes a while to charge. You've got to get like, thousands of volts difference between the two ends of the tube. And right now you're dealing with 110 volts. So you need to give your light a chance to build up that really high voltage. And it's doing it by charging a capacitor. But, it's weird. With lights, they don't call it a capacitor. They call it the ballast. So if you go to a Lights or Us store and you say, hey, I need a new ballast for my lights, well, in your mind, think, well, it's really the capacitor. They don't call it the capacitor. They call it the ballast. But anyway, that's what you do. That's what you're waiting for. You're waiting for the voltage to get higher. Okay, great. So that's the Bohr model of the atom. And the weird thing is it takes very specific energies to make this happen. Okay, so let's go through this until we get to example 4, or probably, to number 5, where I can start talking about energy level diagrams. Question? Okay. In fact, or maybe, okay, let's go. When you excite a gas, it gives off light at very specific frequencies called a line spectrum. Oh, I didn't put any little spaces for you to write stuff here, did I? Okay. Niels Bohr postulated that this was because electrons that orbit the nucleus spend most of their time in stationary orbits or stationary states, where their average distance from the nucleus remains unchanged and they do not radiate any energy. That's another thing Niels Bohr said that kind of goes counter to classical physics. In classical physics, you couldn't have something orbiting forever and ever. Eventually, the orbit starts to decay. Eventually, the electron should fall into the nucleus. But according to Niels Bohr, no. I mean, this electron is in a stationary orbit. It's just going to keep orbiting like this forever and ever and ever. And if you excite it, now it's in that orbit, and it can stay there forever and ever and ever. But it might fall to the lower energy state, and it stays there forever and ever and ever. These are stationary states. They orbit here, they orbit there, but nowhere in between. And so these orbits are discrete sort of orbits. You're there, or there, but nowhere in between. Okay. Number 3, when a particular amount of energy is given to the electron, whether through collisions of voltage being applied to the gas or electron being hit with a photon of particular frequency, the electron will jump to a higher energy level and occupy an orbit farther from the nucleus. That's what you saw there. When an electron falls from a higher energy to a lower energy, it will emit a photon of a particular energy, which means a particular frequency. Okay. Now, the last thing I want to do is show you the energy level diagram, and then we'll do, on our next time together, Thursday, we'll start with example 4. So here we go. The energy level diagram. Here's what they do. The energy level diagram is just the y-axis. lowest energy state. That would be the stationary orbit that's closest to the nucleus. And we call it the n=1 state. Those of you who have chemistry, what do we call that state? It's got a special name. Yeah, it's called the ground state. So this is the ground state. And then the next energy level is the n=2 state, and then the one above that is n=3, and then n=4, and then n=5, and then, you know, boom, 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 until pretty soon you get n=infinity. We assign energies to these states because these energies tell you how much energy is required to bump your electron from the n=1 state to the n=2 state, or the n=2 state to the n=3 state. But here's the weird thing. If I'm going to be at the n=infinity state, that is, my electron is going to be infinitely far away from my proton. And you guys know, how much electrical potential energy would my electron or proton have if they're infinitely far away from each other?
0.
0. So you get this weird thing, when you put the y-axis as energy, the energy at the n=infinity state is 0. 0 electron volts.
0 is infinitely small, -1.
And tell me, as the electron gets closer and closer to the proton, what happens to the electrical potential energy? Does it become more positive or more negative? Yeah, more negative. And so it turns out that the electrical potential energy, when you're at the ground state, is -13.6 electron volts. This is for the hydrogen atom now. I'm dealing with just the hydrogen atom. So tell me, how much energy would I have to give a hydrogen atom to make an electron go from the ground state to the n=infinity state? How much energy would I have to give it? Yeah, thank you, 13.6 electron volts. I hit it with a photon of 13.6 electron volts energy, and it'll propel this electron from the ground state to infinity. So there's another name for this 13.6 electron volts. What is it called? Yeah, the ionization energy. And this n=infinity is the ionization state. And for a hydrogen atom, 13.6 electron volts is the ionization energy. Because you just expelled that electron from the atom. By the way, these higher states, they get a name as well. So that's just for that guy. So the higher states, if that's the ground state, what are the higher states called? Yeah, good for you, Joel. Yeah, excited states. For those of you who have or have had AP chemistry, these are the excited states. And so this might be -3.4 electron volts, and this is -1.51 electron volts. This is for the hydrogen atom. This is -0.85 electron volts. Okay. So the last thing I'm going to do is I'm going to ask you one question, and then we'll continue this tomorrow, or Thursday. Tell me, how much energy is my photon going to have? If I hit my hydrogen atom with a photon, and I want it to rise from the n=1 state to the n=2 state, how much energy is that photon going to have? How many electron volts of energy?
Subtract.
Becca, what do you say?
10.2 electron volts.
How many breather? 10.2? Yeah, that's it. That's how you read these energy diagrams. You get the difference in these two energies, electrical potential energies, and that's how much energy you're going to have to supply to make this guy jump to this higher electrical potential energy. All right, hey, we're done. On Thursday, it's going to be really good. We're going to do this, and then we'll do E=mc squared, and then we're lost.
Yay.
That out for
Well, that's all.